This is Physics, Chapter 6, Section 2, and this has to do with circular motions. No shout out, because I can't remember who I need to give shout outs to, so we'll figure it out anyway. Uh, Big thing here you need to remember about circular motion is when we start talking about this, the object is accelerating towards the center. Even though it's never getting any closer to the center, we say that the acceleration is towards the center, and that's going to help us figure out the forces and the unbalanced force, the net force, and all that type of thing. So we were going to ask why an object moving in a circle is said to be accelerating, and what this whole thing about centripetal acceleration is, and what causes centripetal acceleration, and so on. Remember, we're going to be talking about average velocity. We're going to be talking about the change in distance over time, and we want to look at uniform circular motion. That's when it's at a constant speed. We're going to talk about centripetal acceleration and centripetal force. So let's take a look at this circle and see if I get it to play.
Consider an object moving in a circle at a constant speed, such as a stone being whirled on the end of a string. Is the stone accelerating? Let us examine an object in uniform circular motion. Uniform circular motion is the movement of an object or particle trajectory at a constant speed around a circle with a fixed radius. The position of an object in uniform circular motion relative to the center of the circle is given by the position vector as shown here. As the object moves around the circle, the length of the position vector does not change, but its direction does.
Keep in mind that the position vector then is a length, it's a distance. It's measured in meters or some variation on that.
To find the object's velocity, you need to find its displacement vector over a time interval. The change in position or the object's displacement is calculated by subtracting the two position vectors.
Okay, remember we're going to reverse R1 if we want to subtract R1. So we're going to take the final position vector R2 and we're going to subtract R1. And so now we're going to connect this up here. So you'll see. And now we have
You know that a moving object's average velocity is the displacement of an object divided by the time interval in which the displacement occurs. So for an object in circular motion, velocity is equal to the displacement of an object in circular motion divided by the time interval in which the displacement occurs. The velocity vector has the same direction as the displacement, but a different length. You can see here that the velocity is at right angles to the position vector, which is tangent to its circular path. As the velocity vector moves around the circle, its direction changes, but its length remains the same. Let us now find out the direction of the object's acceleration. The figure here shows the velocity vectors at the beginning and end of a time interval. The difference in the two vectors is found by subtracting the vectors, as shown here. The average acceleration is in the same direction as delta v, that is, toward the center of the circle. Repeat this process for several other time intervals when the object is in different locations on the circle. As the object moves around the circle, the direction of the acceleration vector changes, but its length remains the same. Notice that the acceleration vector of an object in uniform circular motion always points in toward the center of the circle. For this reason, the acceleration of such an object is called center-seeking, or centripetal acceleration.
Okay, so it's accelerating towards the center, but it's never getting any closer to the center because the motion is actually trying to take it away from the circle, and then the acceleration towards the center simply just changes its direction each time. So that's the idea. Okay, so let's do a little bit of math with centripetal acceleration. If we know that the angle, that the vectors for r and r2, it's the same change as v1 and v2. So the angle between r1 and r2 is the same as the angle between v1 and v2. So we say the change in r over r, which would give us the angle. If you remember your geometry, that's basically the chord and the internal angle, is the same for both of these numbers. Okay, the angle is the same for both of these, so we could set these equal to each other. If we divide both sides by t, we now have delta r over delta t. We have delta v over delta t. Delta r over delta t is velocity. The change in velocity over time is acceleration. So now we can plug in velocity over here for the delta r over delta t, and we get velocity over r is going to be equal to acceleration over v. If we multiply both sides by v, we end up with the acceleration is equal to v squared, the velocity squared, times the radius of the circle. So now if we know what the velocity is, if we're given a velocity, if we're given a radius, we can use that to solve our problem. Centripetal acceleration is always towards the center of the circle. Okay, you could take this one step further by talking about the time. If we want velocity, it has to be over time. And so one way of figuring out the velocity is, in general, is if it makes a full circle, if it's gone the circumference of the circle, 2 pi r, that tells us a distance that is traveled. If it travels that over, and if it does that during a period, or if t equals how long it takes to do one revolution, then we can basically set 2 pi r over t. We're going to substitute that velocity in for v squared, so we have to square this whole mess. The r's cancel, and we end up with 4 pi squared r over 2t, or over t squared. I don't particularly care for this equation. I'm going to show you a little bit easier way, I think. If we just focus on the fact that we have the acceleration is the velocity squared over r, then let's just figure out what the velocity is by figuring out the circumference of the circle, and if we're given the period, how long it takes to do one revolution, we have 2 pi r over t. Substitute that in for the velocity, I think is easier than doing that other equation. So for instance, if I say a 13-gram rubber stopper is attached to a 0.93 meter string, and the stopper is swung on a horizontal circle, makes a revolution 1.18 every 1.18 seconds. If I want to find the acceleration towards the center, first of all, I'm going to figure out the circumference of the circle, 2 pi r, and so that means that for one revolution, the rubber stopper will go 5.84 meters. And so if I want to figure out the velocity, I take that 5.84 meters divided by how long it takes to go around once, 1.88 seconds, and I get 4.95 meters per second, the velocity. I plug that in for velocity squared over the distance, and if you go ahead and do that on your calculator, 4.95 squared divided by 0.93, you're going to find it comes out to be 26 meters per second squared, which is the acceleration. So we've just figured out what the acceleration is. Acceleration of an object moving in a circle is always in the direction of the net force on it. So if we have the net force is always going to be towards the center, and it could be provided by any number of agents. For instance, you see the guy swinging that Olympic hammer, swinging on the force. The force is the tension on the chain connected to the massive ball. So that chain's exerting a force, and what are we going to call that force? We're going to call that force centripetal force, this force resulting from centripetal acceleration. Okay? If we know what the force is, then we can figure out, and we know what the mass of the object is, then we could figure out the acceleration due to the force applied on it, and we could figure out we could figure out the force then. So force is equal to mass times acceleration. So if we wanted to go back to our problem, we said that the stopper weighs 13 grams, and we now want to find the magnitude of the tension of the string. In other words, the force net. What is the force that's dragging it in towards the center or causing that centripetal acceleration? We now have an equation that we could plug into. We know that the acceleration is 26 meters per second, so we're going to plug in that for the acceleration. We know that the mass of the stopper is 13 grams. We're going to plug that in for mass, convert it to kilograms first. We multiply it out, and we find that the force is a 0.34 Newton force is pulling the stopper in towards the center. Centripetal acceleration then involves you always want to figure out a coordinate system to use, and for circular motion the direction is towards the center of the circle. So rather than labeling the axis of y or x, we're going to call it c for centripetal acceleration. The other axis is in the direction of the velocity or tangent, so we're going to call that tang. Centripetal force is just another name for the net force of the centripetal in the centripetal direction, or the center seeking direction. It is the sum of all the real forces, those which you can identify agents for, that are acting on the object. Now, just a note about this idea of something called centrifugal force. This is actually a fictitious force. This force does not really exist. Newton's law says that you're going to continue to move in the same direction with the same velocity unless there's a net force acting on you. If you're a passenger in a car, you might feel like there's a force that's trying to throw you out. And in fact, if the door were to open halfway around the curve, you would be thrown out of the car. And you say, well, that's due to centrifugal force. No, centrifugal force, the reason why you get thrown out of the car is because you're trying to travel in the same direction. If the outside of the car is no longer forcing you to move in, if there's no normal force exerted by the car door to keep you in or the seat belts to keep you in, then you're simply going to travel in the same direction that you should be traveling. There is no force that's causing that. So the so-called centrifugal force or outside force is actually a fictitious, non-existent force. You feel as if you're being pushed only because you're accelerating relative to the surroundings around you. And the force that you feel is the door, the normal force of the door pushing you in towards the center of the circle, someplace located by these trees. There is no force that's trying to push you out of the car. You simply want to travel in the same direction. So that's it.